So for inferential statistical tests, so far we've only talked about the z-test. And the z-test is not something that's actually done very often by psychologists or researchers generally, because usually you don't know the population mean and the population standard deviation for whatever research project you're working on. So from here on in the class, what we're going to do is go through one after another. We're going to go through different inferential statistical tests. And from here on in, they're all going to be tests that are often used, or more often used than the z-test. Some are going to be very common, but we're also going to start off with the ones that are simplest, the ones that are most similar to the z-test, and then we'll get more complicated. And so the first test we're going to talk about is called a single sample t-test. It's also sometimes called a one-sample t-test. And you use a single sample t-test when the population mean is known, just like it was for a z-test, but the population standard deviation is unknown, right? Because we need this information to create that population distribution. So a z-test can handle the situation where you don't know the population standard deviation. And the example we're going to be working with here is the research question, research hypothesis. Do SUU students eat more pizza than Americans generally? And for this example research question, the null hypothesis is going to be that there's no difference. The null hypothesis is the dull hypothesis. So in that case, the population mean for how much pizza SUU students eat is going to be exactly the same as the population mean for Americans. And I have the population mean at 46 slices per year. And I got that information off of blog.slicelife.com. So we'll just assume for this example that this is the accurate population mean for Americans, that Americans eat 46 slices of pizza a year. All right, so now we're going to work through an example of a single sample t-test. Right. And so to do this, you need, the first step is to write out your null hypothesis, and recall in our case that is that the number of slices of pizza eaten per year by SUU students is the same as that of Americans generally, which is, we're going to say 46. So we're going to say the population mean of slices eaten per year is 46. And the t-test is set up just like the z-test, and there's only a few things that differ. And what I'm going to try to do is, for the things that are different, I'm going to use a different color. And the things for a t-test that are the same as the z-test, I'll use black. Right? So the next step would be to draw the population distribution. Okay, so that's going to be over here. We're going to assume it's a normal distribution like we did before. This is the population distribution. This is individuals. Individuals. Remember, this is the population where we're getting our sample if the null hypothesis is true. And so for this, we know its mean is going to be 46, but we don't know the population standard deviation. So we're going to come back to that in just a second. So this would be something I could put in red. This is different. All right, so the third step is to draw the sample distribution. In this case, we'll say the sample size is 100. The sample mean is 56, and the sample standard deviation is 10. And we'll say it looks something like that, right? So this is the observed sample distribution. And these are all frequency distributions. these are individuals, just like the population was. And remember, whenever you're doing your research, this is the only data you ever have. This is the only distribution you can actually draw from your data. All of this stuff is done behind the scenes by whatever statistical program you're using. But to understand what the statistical program is doing, we have to draw all this stuff out to make all of the steps that it's doing explicit. All right, so now that we know our sample data, what we're going to do is, remember, for our population, we didn't know what the population standard deviation is. But our sample gives us a guesstimate of what the population standard deviation might be. And what we're actually going to do is we're going to use our sample standard deviation as our best guess at our population standard deviation. So we're going to say our population standard deviation, our best guess, our estimate, so this is going to be sigma hat, is equal to our sample standard deviation, which in this case is equal to 10. So here we're going to say the standard deviation is 10, because we don't actually know what the population standard deviation is, but given our sample data, right, our sample data is likely to have the amount of variability, or the standard deviation will reflect this. So if our population were really spread out, we'd expect a sample that's more spread out. If a population was really squished in, we'd expect a sample that's squished in. Right? So our sample standard deviation is going to give us some sense of how spread out our population is, and that's going to be our best guess. And so we're going to use our sample standard deviation as an estimate of our population standard deviation. And once that is done, pretty much everything else is going to be very similar to the z-test. And I'll point out where it's different. So the next thing we'll do is draw the sampling distribution. So that'll be here. This is our sampling distribution, right? And these are the expected sample means due to random sampling from this population, if the null hypothesis is true. So again, we're hoping to find that our sample mean is the kind of sample mean you don't expect from this population due to random sampling. We're hoping it's so unlikely that we'll reject the null hypothesis. Okay, so we can draw our sampling distribution here. And just like with the z-test, the means are going to be the same. And we have the same formula here for the standard error, except for now, we're using our sample as our best guess. So we're actually going to switch this, and now we're going to, since we're using our sample as our estimate, we're going to put the s here instead of sigma. So this isn't based on the known population standard deviation. It's based on an estimate from our sample. That'll be s divided by the square root of n. All right. So really this is exactly the same, except for all we've done is started off just plugging in our sample standard deviation for our population, but the formulas are all the same. They're very superficial changes. So 10 divided by the square root of 100. So the standard deviation of this distribution is 1. The standard error is 1. For a z-test, when we knew the population standard deviation, the sampling distribution was a normal distribution, but for a t-test, it's no longer normal. Remember, this was a normal distribution, so we could use the z-table to calculate our probabilities. When the population's standard deviation is estimated based on the sample, that adds more uncertainty into the calculation of this distribution. And it turns out that it makes this a little platykurtic. It's a little squished out. And so what people did is they figured out exactly what the shape would be like and calculated the critical values. And there's the table that we use for determining the critical values is called a t-table. Right? Before we had a z-statistic and z-criticals. Now we're going to have a t-statistic and a t-critical. So everything that was a z is now going to be a t when you go from a z-test to a t-test. So the fifth step, just for the t-test, just like it was for a z-test, is to determine our critical regions and the critical values to go with it. Right? So of course we're going to do a two-tailed test like you pretty much always should. Alpha of 0.05, just like before. Right? So now we've got to figure out what are our t-critical values. So those are going to be the number of standard deviations over on a t distribution. So we'll have one above and one below. So for this, you need to look at a t table. And when you look at a t table, it's going to ask you what the df is for your test. The df stands for the degrees of freedom. And the formula for the degrees of freedom for one sample t-test is really easy. It's the sample size minus 1. So in this case, we have 100 minus 1 is 99. So our degrees of freedom are 99. And I'll explain later on a little bit more about the shape of the t distribution and more about degrees of freedom. I'll come back to that later on. Right now, I just want to go through the steps. So to determine your t critical values, you need to know the degrees of freedom to use the table. So you'll go to the degrees of freedom table, and notice the larger your sample size, the larger your degrees of freedom, and also the larger your sample size, the better your guess at the population standard deviation based on your sample. Just because the larger your sample size, the more accurate the more your sample statistics will reflect those population parameters, more accurate they'll be. And so if you go to the table and this number's not there, what you want to do is go to the number that is there, that's the next one that's smaller. So if there's a degrees of freedom 95, that's what you're going to want to use to determine your t critical. And the reason you don't want to go larger is because if you go to a larger degrees of freedom, that's saying that you have a larger sample size than you do, and you end up with an alpha greater than 0.05. So we're going to be conservative, and we're going to say if the table doesn't have our degrees of freedom, we're going to use a smaller degrees of freedom so that our alpha isn't too big. So that'll have our t criticals be out further than if we had a larger sample size. So I looked up on my t table the t critical values, and I got for them, the top one is 1.986, and the bottom one is negative 1.986, where a t distribution is going to be symmetrical, just like a z distribution. Notice these are very similar to the 1.96 that we had for a z table. And that's because the sample size is really large. And in fact, as the sample size approaches infinity, t critical values get closer and closer to 1.96. And with an infinite sample size, the t critical is 1.96. Because with an infinite sample size, you actually know the population parameter. And then you've got yourself a z test. The sixth step will be to calculate our test statistic. So for a z test, that was called a z statistic. For a t test, it's called a t statistic. But a t statistic is exactly the same thing as a z statistic. It's just how many standard deviations our sample mean is away from the mean on this distribution. So it's the z-score of our sample mean on this distribution. So the formula is going to be the same as it was for a z statistic. And that is the sample mean minus the mean of the sampling distribution. But now we're going to divide it by, well, we're still dividing it by the standard deviation of this distribution, but now we're using a value that's estimated based on our sample. Because we don't actually know, the population standard deviation, so we don't know this. But mathematically and conceptually, it's really pretty much the same thing. Once we've done that substitution early on, all of these steps are the same as the z. So now we'll calculate our t statistic. Our sample mean is 56. The mean of the sampling distribution is 46. The standard deviation of our sampling distribution is 1. 10 divided by 1, 10. So our t statistic, in this case, is 10. So that means our sample mean is 10 standard deviations over on this distribution. So if this is about 1, 2, that's about 2, 4, 8. So on this distribution, it's way over here. So this is the kind of sample mean that's very unlikely to have come from this population due to random sampling, right? This is the kind of sample means that you expect. So this would be exceptionally unlikely. The probability would be way under 1% or 0.01% even. And so like ultimately we're going to decide that this sample probably came from a population that's more over here. And now the next step is to decide to either reject the null hypothesis or fail to reject the null hypothesis, right? And just like we did with the z-test, for a t-test, we're going to compare our t-statistic with our t-critical values, right? Our t-critical was plus or minus 1.986. A 10 is much more extreme than 1.986. Therefore, we're going to decide in this case to reject the null hypothesis. All right, so we're rejecting that the population mean of SUU is the same as the population mean of Americans. So another way to say that is we're rejecting the idea that the population mean for SUU students is 46. If we were going to make this decision using software like SPSS, what we would do instead of comparing our t-critical with our t-statistic is SPSS would tell us a p-value. I don't know what it actually would be in this case, but it would be probably something like that. And remember what we do to decide about rejecting the null hypothesis or not. With the p-values, we compare that directly with our alpha. And if our p-value, our probability, is smaller than our alpha, we reject the null hypothesis. And again, you'll always come to the same decision comparing your p-value with alpha as you do comparing your t-statistics with your t-critical. Okay, we've decided to reject the null hypothesis in this case. If we would have failed to reject, when we interpret our findings, if we would have failed to reject, we'd have said, oh, the study is inconclusive. It's possible that SUU students eat the same amount of pizza as Americans. We can't quite tell. Our data is inconclusive. But in this case, we actually rejected the null hypothesis. And so now, what we're going to do is we're going to say, well, SUU students ate 56 slices of pizza per year, and that is more than Americans. So our interpretation is going to be SUU students eat more pizza than Americans. And the reason we said more, not less, is our sample mean is greater than the American mean. So if our sample mean would have been smaller than this, 36 for example, we still would have rejected the null hypothesis because it's still, the test statistic still would have been 10 because it's 10 away, except for it would have been a t of negative 10. We still would have rejected the null hypothesis, but then our interpretation would have been SUU students eat less pizza than Americans, right? And we could have also written out this interpretation symbolically. So SUU students eat more pizza than Americans. The population mean for SUU is greater than the population mean of Americans. So this mathematically says the same thing as our interpretation here. The next thing we can do is calculate our effect size. And it's also going to be Cohen's d like it was for the z-test. And remember, this is how many standard deviations our sample is over at the population level. And we don't know the population standard deviation in this case, but what we do have is our sample estimate. So we'll put that on the bottom. So we'll calculate Cohen's d up here. So that was the sample mean minus the population mean divided by, now we have to use our population estimate based on our sample. So Cohen's d equals 56 minus 46 divided by 10. So 10 on the top, 10 on the bottom. So our Cohen's d is 1. So this means that our best guess is that using our sample mean as a point estimate of our population mean for SUU students, that SUU students their mean is 1 standard deviation over on this distribution. So our best guess is that this is where the mean of SUU students is. It's 1 standard deviation over. And recall for Cohen's d, the small, medium, and large reference points are plus or minus 0.2, plus or minus 0.5, and plus or minus 0.8. So a 1 is a large effect size. So if this is what our data looked like, we reject the null hypothesis. We decide that SUU students eat more pizza than Americans, and the effect size is a large effect size in this case.